Hello everybody and welcome to the final video for pharmacy calculations. There's only one topic in this video. It's the only new topic on your final quiz, and hopefully you've accrued enough points this semester where you don't need to take the final. But with that, let's get into isotonicity. So what does it mean to be isotonic? Essentially in our body, whether this be our blood, the fluid in our eyes, really anywhere there's a fluid, there's always kind of a standard the cells in our body like. And usually when we talk about that standards in the context of pharmacy, we're talking about blood isotonicity, right? Because something like the mouth per se isn't super sensitive, so if we're giving an oral solution of a drug, we don't really need to worry about it being isotonic because it's not going to like cause the cells any damage because they're so hardy already. We put various like hot and cold foods in our mouth, those cells are very resistant. But for something like an eye or something like the blood, those are more sensitive just due to the fact that they're not necessarily exposed to the outside environment as much. I guess the eye is, but it also things aren't really meant to go in your eye naturally. So there's kind of a range of amount of things in solution that they're used to, and otherwise they freak out. So what happens if you do a solution that's too much water per solute? This is called a hypotonic solution. And essentially what this will do is, since water will follow solutes in a solution, if there's more solutes in our cell, water will be pushed into the cell, and that can cause the cells to swell or even burst. Alternatively, what happens if we use a solution that has too many particles, too many solutes on a cell? This is known as a hypertonic solution, and this essentially the opposite will happen, right? Water will be pulled out of our cells due to the fact that it's following the solutes in the solution we want to give, which aren't great. Both can kill cells. And obviously, it's more likely to kill cells at more extreme values, but we like to avoid it entirely, and we want what's called an isotonic solution. Isotonic or isotonicity, and that's kind of what this is. So when we have a solution that we want to give to the blood, to the eyes, we want it to be in this isotonic range. And you can see up there it's a range, right? 275 to 300. I believe this is roughly blood isotonicity. Usually that's more 285 to 300, but since this is a very general introduction, you'll learn more about this in fundamentals of pharmaceutics. It's pretty, this is pretty much at the most basic level you can have it. So something really important to note is most of the time, I would say like 80% of the time, you will be using an NaCl solution, right? Salt is very inert, it's very basic, it's very cheap, it's easy to sterilize. So this is what we generally like to do when we're preparing an isotonic solution. So how do we do that? So what we do is first we need to know that the isotonic value of sodium chloride is 0.9%. And if you recall from the previous videos in class, that 0.9% means 0.9 grams per liter or milliliter, right? So when we're making a solution like this, it's actually really easy if we have the volume we need to start with, because then we can just find out how much sodium we need to add in general. You can see the solution has a QS for add water. When it's a sodium solution, it's pretty much also implied to be QS add sodium as well. So how do we set up a problem like this? First, we need to find out how much solute is actually going into our solution. And the way we can do that is we can do 0.009 grams of NaCl times 30 milliliters. And if you don't see how I got 0.009, remember that there's a percent, so you'd have to divide by 100. So with that, we can multiply this to get our final solution. It needs to have 0.27 grams of sodium. But you can see we have these other substances in here that aren't sodium. And sodium's a really nice ion, right? If you remember from like the equivalence video and the osmolarity video, sodium breaks up really nicely into two ions. It doesn't really do anything, it never stays together. And that changes when you're talking about organic molecules. They're very hard to characterize. So what was invented is what are called equivalents. Um, and how these will essentially work are for each value of sodium, these have all been characterized. For example, chlorbutanol, it's 0.24 equivalents of sodium, right? And the reason for this is usually the number is a little bit lower, and because sodium will break up really cleanly into two parts, these weak acids will usually stay as one part, so it'll usually be lower. So essentially what we can do is we can multiply the masses of each of these drugs. I'm going to convert these to grams as well to keep our units consistent. So we have zero point 0.1 grams of chlorbutanol times this 0.24, and we're going to subtract this, right? Because this is the total amount we need in solution, and we're adding what we already have. So this will allow us to find our sodium. So we also have 0.05 grams oxytetracycline, and you can see that has 0.12 equivalents. So we multiply that by 0.12. I'm going to plug this into my calculator really quick. So the final answer we get when we subtract all that out is we get 0.24 grams of sodium chloride. And that's our final answer for a problem like this. This is how much we need to add to make the solution isotonic, which makes sense. 0.24 grams is pretty low, but also 0.9% of a solution is also pretty low. So that's just, it kind of makes sense, right? It's very straightforward when it comes to just sodium in the problems. On the next slide, we'll talk about some contingencies that make it a little more complicated. So I want to do one more example of a simpler one before we move forward. So how many grams of NaCl? Remembering our rule of 0.9, so if we do 0.009 grams, because remember from the previous slide we talked about how 0.9% is this per milliliter, and then times 100 milliliters, we get, I probably don't need to plug this into my calculator, but I'm so paranoid about checking it. Yeah, it's 0.9. I don't even know why I bothered to do that. We get that we need 0.9 grams of sodium. So what we do is 0.9, right? NaCl. We have our phenylephrine, which is over here on the chart. You can see that's 0.32. And I'm going to divide by 1,000, remember, to get to grams. So we actually just have 1 gram phenylephrine times 0.32. And that's subtracted. And then we also have 0.5 grams chlorbutanol, which was also in our previous problem, which is still 0.24. And then the rest of this is just telling us to make it as directed. So those are only 2 ingredients again. So we do this math really quick. 0.9 minus 0.32 minus 0.12. We get 0.46 grams of sodium chloride as our final answer here. So again, pretty straightforward, just being able to read that table, which is in alphabetical order. Dr. Hegner is never going to give you an ingredient that's not on that table. You don't ever need to memorize any of these. Yeah. So now let's say we, for whatever reason, we don't want a solution that uses sodium chloride, right? Maybe sodium chloride causes something to precipitate. That's really the only situation I can think where you wouldn't use sodium chloride. Because again, it's very inert for the most part. So what we could do instead is the equivalency table actually works 2 ways. While it shows things that are equivalent to sodium chloride, it also shows things sodium chloride is equivalent to. So let's say we had our 0.46 grams of NaCl, right? Let's say we wanted boric acid instead. How would we go about that? We could see boric acid's up here in the table is 0.52. All we'd have to do for that is take our 0.46 grams of sodium chloride. Divide it by that 0.52 of boric acid. And these numbers over here, by the way, are more or less unitless, so you don't really need to worry about doing dimensional analysis with them. When we do that, we get 0.88 grams boric acid. So you can see here, this number is higher than grams of sodium chloride. Again, there's multiple reasons for that, because molar masses are a factor, amount of ions it breaks into are a factor, just all these moving bits and parts. And that's why the equivalent value is really nice, just because it's something that's already been characterized and calculated for us. And then for the last one, this is probably the most complicated type of example you'd see, because there's two things we need to do essentially. We have 15 milliliters, which is our final solution volume. And then we have oxymetazoline, and instead of giving us a mass, it gives us like a strength, which is fine because we can get mass from that. It's just an extra step to the problem. So, and then this one's boric acid as well. So this kind of has all the moving bits and parts. So what can we do first? We can still do our sodium value times 0.09%, right? Because these equivalents are all based off of sodium. So I would always still make that your first step no matter what. So we have 0.009 grams sodium chloride, sorry if I've just been saying sodium this whole video, and then times 15 milliliters. When we do that, we get 0.135. grams of sodium chloride. Now we need to find the strength of oxymetazoline. So very similar to what we just did for sodium, actually, we can do 0.005. Remember, because 0.5% divided by 100, that's how we get that, times 15 equals 0.075 grams of oxymetazoline, and then we also need that's equivalence value. So up here you can see I already circled it, it's 0.2. And since this is our only ingredient, right, boric acid's like our final base in the solution, this is actually the only thing we need to subtract. All the other problems I think I've shown you so far have had two ingredients, this one only has one, essentially. So we can do that 0.135 minus 0.075 times 0.2. We get that we would need, if we were using sodium chloride, 0.12 grams of sodium chloride. But remember, we want that boric acid again, which is all the way up here. That's our 0.52. So we can divide this 0.12 by 0.52. We get a final answer of 0.23 grams boric acid. And with that, that's pretty much everything on equivalence. That final problem is about as complicated as they get. So if you can understand that and follow that, you should do pretty well for that final quiz. And also it is a comprehensive quiz, I believe, so know the other videos as well, and the material talked about in class. But with that, thank you so much for watching this video series, and good luck on your quizzes and exams.